Welcome back to Beyond Time Conversations. Today, we are joined by a man whose name is synonymous with the very laws that govern our universe. Sir Isaac Newton, many people today know you as the figure who completed the foundations of modern science. But before all of that, how would you describe yourself as a person and as a thinker?
To understand the man, one must look toward the quiet fields of Woolsthorpe, where my life began in the shadow of the English Civil War. I was born into a Puritan family, a fatherless child who was perhaps not well suited for the life of a farmer, as my early attempts to manage the family estate were quite unsuccessful. I have always been at my core a problem solver extraordinaire. Whether I was faced with the reconstruction of Solomon's temple from biblical accounts or the mathematical determination of a planetary orbit, I would stay with a single problem until a solution was found. I tended to compartmentalize my interests, focusing with intense concentration on one subject at a time, be it optics, alchemy, or theology, often keeping these pursuits in private for decades. I was a man of solitary research and careful reflection, wary of public disputes and often choosing to withdraw from the world when my work faced challenges that felt more like personal attacks than intellectual inquiries.
It's fascinating to hear you describe that inward focus. How did your early life and those formative years at Cambridge shape the way you approached knowledge and inquiry?
My arrival at Trinity College in 1661 marked a transition from a classical education centered on the rhetoric and logic of Aristotle to a self-directed exploration of the moderns. By 1664, I had begun reaching beyond the standard curriculum to teach myself mathematics and philosophy, reading the works of Descartes, Wallace, and Viette. However, the most defining period was likely the mid-1660s during the plague years, when the university closed and I returned to Woolsthorpe. In that period of isolation, often called my annus mirabilis, I developed the foundations of the calculus, my theories on optics, and the relationship between the inverse square law and planetary motion. These years taught me that true discovery requires an unshackling from established authority. I learned to value mathematical theory and meticulous experimentation as the twin pillars of inquiry, ensuring that my conclusions were always anchored in the empirical world.
You speak of moving beyond established authority. Galileo, of course, transformed science by placing observation and experiment at its center. What did you inherit from his work? And where did you feel compelled to go beyond it?
Galileo's commitment to the empirical world as the ultimate arbiter was a cornerstone of the natural philosophy I embraced. I inherited the belief that specific phenomena should decide each element of a theory. However, I felt compelled to go beyond the method of hypotheses. Many of my contemporaries would put forward a hypothesis that reached beyond known phenomena and then simply test it by deducing observable conclusions. I found this insufficient. I insisted on limiting the provisional aspect of theory as much as possible. I believe that propositions should be gathered directly from phenomena by induction and taken as true until other phenomena made them more exact. While Galileo placed experiment at the center, I sought to unify these experiments under a universal mathematical framework, one that did not merely suggest causes, but demonstrated the mathematical laws that forces must obey.
That bridge between experiment and the abstract is your hallmark. You believe that nature could be described through mathematics. Why did mathematics, in your view, offer such certainty about the natural world?
Mathematics provides a rigor that prevents the mind from wandering into the realm of occult powers or unfounded hypotheses. In my view, the only way to render limits and physical laws rigorous was to ground them in geometry. While others, like Leibniz, sought to transform mathematics into a discipline of symbol manipulation, I remained opposed to that path. I believe that by extending geometry to incorporate limits, we could describe the uniform circular motion and the trajectories of bodies with a certainty that mere words could never achieve. For me, mathematics was not just a tool, it was the language through which the empirical world revealed its underlying structure, allowing us to move from the specific phenomena of a falling apple or a revolving moon to a universal theory of gravity.
In the Principia, you presented laws that seemed to govern the entire universe. Were these laws something you believed humans discover, or something the human mind imposes on nature?
I have always maintained that these laws are gathered from the phenomena. They are not impositions of the human mind, but rather inductions from the evidence arising from experiments. In the Principia, I stopped where evidence was wanting. For instance, I did not affirm whether the cause of gravity was mechanical or non-mechanical, because I lacked the experiments to decide the question. To impose a cause without evidence would be to trade science for a perpetual miracle or a baseless hypothesis. Humans discover these laws by observing the specific details of the world, the tides, the motion of comets, the orbits of planets, and then generalizing those observations into universal propositions. The laws are there, written in the frame of nature. Our task is merely to be diligent enough in our mathematical and experimental labors to read them.
Your work often reflects a careful balance between natural law and divine order. How did you understand the relationship between God, nature, and mathematical law?
I saw no conflict between the mathematical order of nature and the existence of a deity. In fact, I devoted as much effort to theology and biblical studies as I did to physics. My study of the doctrine of the Trinity led me to question the validity of much central church doctrine as I sought a more primitive and radical understanding of the divine. I viewed the universe as a system that reflected a divine order, but I did not believe that God acted through perpetual miracles that bypassed natural law. Instead, the mathematical laws I discovered were the very means by which the world was sustained. While I am sometimes portrayed as a wild religious zealot for my prophecies regarding the end of the earth, my private writings show that I saw the study of nature and the study of Scripture as two paths to the same ultimate truth.
Today, we increasingly rely on machines to calculate, model, and even reason on our behalf. If such tools had existed in your time, what would you have been most cautious about?
Based on my historical opposition to Leibniz's vision of mathematics, I believe I would have been most cautious about the surrender of geometric rigor to mere symbol manipulation. I was fundamentally opposed to the idea of grounding mathematics in symbols alone. If a machine calculates without the thinker understanding the geometric limits and the physical phenomena behind the numbers, there is a risk of losing the connection to reality. I was a man who revised every page of the Principia with extreme care, often prodded by my editors to reconsider the smallest details. I would fear that a machine might encourage a lack of self-critical reflection. We must be careful not to allow the convenience of a calculation to nullify the need for inductive reasoning grounded in the empirical world.
A powerful reminder that the tool should never replace the clarity of the mind. Sir Isaac, as we look back on your long journey from Woolsthorpe to the Royal Society, what is the one question about the universe you wish you had more time to solve?
I spent many years contemplating the ultimate cause of gravity and the true nature of light, whether it be waves or particles. Though I felt the latter was more probable, I recognized that no experiment in my lifetime could truly decide the matter. I was content to leave those questions open where evidence was wanting, but the desire to find that final, deciding phenomenon remained with me until the end.
Sir Isaac, you have provided the mathematical keys to the heavens and redefined the way we see the world. As we finish our conversation, looking back across your 84 years, how do you hope you are remembered? Not just for your laws, but for the spirit with which you approach the unknown.
I have always viewed myself as a problem solver extraordinaire, someone who could take on a single, daunting problem at a time and stay with it until a solution was found. I would hope to be remembered as a man of careful, self-critical reflection, whose every published word was backed by intense scrutiny. More than the specific laws of motion or gravity, I hope the spirit of empirically driven science persists, the commitment to having the empirical world serve as the ultimate arbiter of truth. I was always careful to stop where evidence was wanting, refusing to affirm causes like the ultimate nature of gravity or light when the phenomena did not yet allow for a decision. If my work has any lasting value, it is because I insisted that we gather our propositions from phenomena by induction, taking them as true only until other phenomena make them more exact. I was a man who sought truth across many fields, from optics and mathematics to theology and alchemy, And in each, I simply tried to follow the evidence where it led, even when it required me to leave the greatest questions of the universe open for those who would follow.
A truly profound legacy of disciplined curiosity. Sir Isaac Newton, thank you for sharing your time and your extraordinary mind with us today. To our listeners, thank you for joining us for this journey through the foundations of our modern world. We hope this conversation has inspired you to look at the stars and the math that moves them with newfound wonder. Until next time, this is Beyond Time Conversations. Good night.